Hi everyone, I'm Lewis from Bygen, and we're on a mission to enable the low-cost production of activated carbon for the betterment of people on the planet. Now, unfortunately, as a society, we're not currently on track to meet our CO2 emissions targets according to the Paris Agreement. And at Bygen, we strongly believe that we're fast approaching a time where active removal of CO2 from the atmosphere at scale is required to help us meet those targets. So how do we do this? So at Bygen, we take common waste streams from the agricultural and forestry industries, like nutshells, sugarcane residues, and sawdust. We use our novel low-temperature activation technology to then convert those waste streams into high-value activated carbon, while also sequestering CO2. So what is activated carbon, you might ask? So it's essentially a black powder that has lots of unique properties, but the major property that makes it useful is its very high internal surface area. So 1 gram of activated carbon contains over 600 square meters of internal surface area. And the analogy we use is if you have a teaspoon of activated carbon, you have the same surface area as a football field inside of it. And all this surface area makes it a really excellent filter. So basically chemicals travel inside the activated carbon where they bind and get trapped and can't be released. And this means it's used in a wide range of applications, including drinking water treatment, polluted soil remediation, and even in precious metal recovery. So all of this surface area comes from the presence of small holes called pores. And the smallest of these pores are called micropores. They're around 2 nanometers in size. That's about 1,000 times smaller than a human hair. And the largest of these are called macropores. They're around about 50 nanometers in size. And it's inside these pores that the chemicals get stuck and can't be removed. And this is what activated carbon looks like, in case no one's ever seen it before. Essentially, it looks a bit like a black powder, but it can also be sold in granular form as well. But it's no understatement, because of its importance in a wide range of industries. Without it, the modern world would not have clean air, clean water, and clean soil. Now, this diverse range of applications means it's got a very large and growing market. About $10 billion worth of activated carbon are used every single year. That's around about 4 to 5 million tons. And it typically sells for between $3,000 to $10,000 a ton, depending on its quality and volume. There are issues, though, with the current activated carbon in the market. So the first of these is what we call the one-size-fits-all approach. So all those diverse applications I showed you earlier, you're basically trying to bind chemicals that have got hugely different sizes, structures, and chemistries. And the current activated carbons offer little to no tailoring to take those differences into account. So customers end up paying very high prices, get relatively poor performance, and the reason that they have to pay so much for it is that the way it's made is extremely energy intensive, needing 1,000 degrees and lots of water. There's also huge social and environmental problems with the activated carbon market as well. The majority of the world's activated carbon is still made from coal. The production process needs lots of fossil fuels as well. It results in huge CO2 emissions and actually some dangerous production conditions as well. And to give an example of this, despite being a very advanced material, which has a wide market, a lot of the world's activated carbon starts out in sites like this, where basically pits are dug in the ground. The feedstock is loaded into them, covered up, allowed to burn under very low oxygen conditions to produce something that looks a bit like charcoal. But this process produces a lot of smoke that's very harmful to the local people. And then that charcoal-like substance is then sent to big centralized production plants in China, Europe, and America, where it's basically fired up to 1,000 degrees with steam. And the steam and carbon react to give you that surface area. So at Bygen, we didn't think this was good enough. So at the University of Adelaide, we developed our technology that we call low temperature activation that helps slash the production cost of activated carbon by up to 60%. So our patented technology allows us to make activated carbon at much lower temperatures, around about 250 degrees. It's an entirely self-sustaining process. We don't need any fossil fuels in our production process. We don't need any harsh chemicals as well. And we have significantly lower capital costs for our equipment as well because of our lower temperatures, which means we can use cheaper construction materials. We've also developed the ability to tailor our products to improve performance by changing the surface chemistry of them. We are able to use cheap and renewable waste products, like instead of coal. And when we do this, we believe our technology is carbon negative. So we sequester about 2 tons of CO2 for every ton of activated carbon we produce. Now, the scale of CO2 emissions reduction that we can achieve is vast. So if we were to replace all of the world's coal-based activated carbon with our sustainable product, we would achieve the same emissions reduction as removing 20 million cars from the roads every single year. It's about 100 million tons of CO2. Now, our first target market for our activated carbon product is in the growing PFAS remediation industry. I don't know how many people have heard of PFAS before, but essentially it's a class of chemicals that are called forever chemicals because they don't break down over time. And one of the brand names is Teflon, so it's one that has non-stick applications. But it's recently been discovered that a lot of PFAS chemicals are carcinogenic, and there's lots of polluted sites around Australia and the rest of the world. And activated carbon is one of the only ways that you can actually clean up PFAS polluted sites. So we have developed a tailored activated carbon specifically for PFAS. And in independent trials, we've shown that we can achieve up to 99% net removal efficiencies for all of the PFAS chemicals that we tested for. And with those results, we've secured offtake agreements for our production facilities with large-scale users of activated carbon. One example of our product being used in the real world, this is at Carlnar Park in South Australia. So the wetlands there are contaminated with low levels of PFAS. We have supplied about 1 ton of our sustainable and tailored activated carbon to that site. And we're working with the CSIRO and floating wetlands to basically incorporate it into plant beds to help remediate that polluted water system. And also drinking water treatment is a huge market for activated carbon. It's used in basically every water treatment plant around Australia and the rest of the world. We have done testing with SA Water, with our tailored water product, and we've shown a doubling of removal efficiency for common water contaminants compared to the current coal-based activated carbon that they use. We've also got targeting emerging and high-value applications for activated carbon. All of the world's supercapacitors currently use activated carbon, but we are actually working with a large lead-acid battery manufacturer to actually incorporate it into their batteries. And one of the things that you can also do, and we are working on, is using our activated carbons to store hydrogen and methane. One of the advantages of using porous materials for gas storage is that you can do it at room temperature, and you can avoid expensive compression processes. So we're getting some really exciting results in this space. So our business model essentially is to identify large-scale waste producers in the agricultural and forestry industries. We then, with our manufacturing partner, design and build a facility for their site. The waste producer pays for it and they own it, and we essentially get paid to market and sell the activated carbon that's produced from that site. So we currently have 2 in-house production plants, the biggest of which can process about 150 kilograms an hour of waste. We're building our 3rd plant right now in South Australia, and we've got a 4th one to come very shortly afterwards. And we have another 4 units in agreements with waste producers around Australia and overseas. And the exciting thing for us is when we get to 12 production units of our target commercial size, we will become the world's largest activated carbon producer. But even more exciting for us is that that's great commercially, but we'll also be actively sequestering CO2 at scale at the same time. So this is our team. So I'm Lewis Dunnigan. I'm one of the co-founders and co-inventors. I have a PhD in chemical engineering, and I used to be a researcher focusing on material science. We've recently appointed Cameron Griffiths as our CCO. I used to be quite senior at Suez, who are a large water treatment company. And also in our site in Thomastown, we have Mitchell Taylor, who's our R&D chemist, and Catherine Shee, who works in sales and marketing. And we recently appointed Joel Phillips as our non-executive director, hugely experienced in the water treatment industry, and we have a great set of advisors in Patrick Seb and Michael Macalino. thanks for listening. If anything was of interest to you, we are currently doing a capital raise, so please feel free to come and chat to me afterwards. Thank you.
I know Peter's watching over me like a hawk, but I'll be cheeky, and if anyone's got a question, happy to take a question. We've got one over there if you want to use it. Oh, there we go.
Sorry, at risk of being a serial pest, a question about what happens once you actually, because it captures the pollutant.
Yes.
Presumably then you need to dispose of that activated carbon in some way, and what happens then?
So in Australia, that is one of the common ways of essentially disposing of it, but you are able to regenerate activated carbon by basically subjecting it to a pretty similar set of conditions compared to how you made it. So essentially you strip off whatever and destroy whatever the contaminant is, and then you get essentially brand new activated carbon out of the same site. So it is possible to regenerate it. It's commonly done in Europe and America, but it's an emerging application in Australia.
We might have to leave it there because I know there's people gathering for the next session, so a round of applause.